In the flight plans for pilots, it's important that the route they log with the control tower that they plan to follow be a continuous line, or in mathematics, what we would call a continuous function. Hi, my name is Tom Atwater, and that's what we will be learning about in today's lesson: continuous functions and composites. Let's start with a definition. Definition of continuity at a point. Interior point. A function y equals f of x is continuous at an interior point, c, of its domain if the limit as x goes to c of f of x is equal to f of c. Now, for an endpoint, a function y equals f of x is continuous at a left endpoint a, or is continuous at a right endpoint b of its domain if the limit as x goes to a from the positive side of f of x is f of a, or the limit as x goes to b from the negative side of f of x is equal to f of b, respectively. Once again, let's look at an example to illustrate this particular definition. Find the points of continuity and discontinuity of the function. Identify each type of discontinuity. Well, first of all, let's look at the domain of this function. The domain of the function, well, we've got square root, which means anything underneath there has to be 0 or greater, which means the domain can start at -3/2 inclusive, and then go all the way up to infinity. So that's our domain. Now, in terms of the square root graph, we've seen this many times, and it is continuous throughout that domain, which also means for all the points not in the domain, which of course would be the points x is less than -3/2, those would be all the points of discontinuity. Now, we can carry this continuity at a point idea to a function over a whole interval, and we can do that as follows. A function is continuous on an interval if and only if it is continuous at every point of the interval. A continuous function is one that is continuous at every point of its domain. Once again, let's look at an example to illustrate these two definitions. Find each point of discontinuity and which of the discontinuities are what we call removable and which ones are not removable, and give your reasons. We have a piecewise function. F of x is equal to 3 minus x, where x is less than 2, and it's equal to x over 2 plus 1 when x is greater than 2. So let's graph this function to help us determine what's going on with continuity and discontinuity. What we know is this graph will go through a y-intercept of 3. It has a -1 slope, which will bring us down to this point where I will put an open circle, and the line is going up like this with a slope of -1. For the second part, we start right here at x equals 2 comma y equals 2. And this time, it's an open circle as well, and the graph is going out with a slope of 1/2. Now, in this example, what we see is that the graph is discontinuous at x equals 2. Right here, that's x equals 2. It's discontinuous because the one-sided limits are different. As we're approaching from the right, this side coming in, it's going to 2, and as we're approaching from the left, it's going to 1. This is what we called jump discontinuity, because it literally jumps between two different one-sided limits. There is also what we call infinite discontinuity, where one or both of the one-sided limits are infinite. And there is also what is called oscillating discontinuity, where the function value oscillates too much for it to have a specific limit. There are some properties of continuous functions that are useful to note. So let's take a look at them right now. Properties of continuous functions. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c. The sums, f plus g, would be continuous. The differences, f minus g. The product, f times g. The constant multiple for any number k, k times f. And the quotient, provided g does not equal 0, of f divided by g. There is one other algebraic way to combine continuous functions, and I want to take a look at that with you right now. Theorem 7, composite of continuous functions. If g is continuous at c and f is continuous at g of c, then the composite f of g is continuous at c. There's another theorem that follows right after this, the intermediate value theorem for continuous functions. A function y equals f of x that is continuous on a closed interval a comma b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 will equal f of c for some value of c in the interval a comma b. Let's look at this graphically. So what we're saying is this: if there's a value y sub naught or y naught which is between f of a and f of b, so here's our value on this function, then there exists a value c that is between a and b. All right, let's apply the intermediate value theorem to an example. Is any real number exactly one less than its cube? So we'll start off by saying, is any real number x exactly, that is, equal to 1 less than its cube? Okay, well, let's get this now in the form x cubed minus x minus 1 equals 0, because that's what we would have to solve in order for us to have a value of x for which this is true. So now let's take a look at the graph and see if that can help us determine what's going on. So this is the graph of x cubed minus x minus 1. And what we can see is that there is a sign change somewhere between 2 and 1. And actually, very specifically, using the calculator to find the 0 of a function, which is under your math key, it yields the value 1.3247, but we can round that off to 1.325. So yes, in fact, there is a value, in this case, a value of c, which is 1.325, such that it's in the interval between 1 and 2. Well, now it's time for you to try a problem. Using the intermediate value theorem, I want you to look at and solve any real number exactly 2 more than its cube. Give any such value accurate to 3 decimal places. So pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did on this problem. Once again, you set up the algebraic part of it. So is any real number x exactly, so equal to 2 more than its cube, x cubed plus 2. So we rewrite that x cubed minus x plus 2 equals 0. We can plug that into the equation editor of our calculator and take a look at its graph, which would be right here. And what we'll notice is that if we use the calculate the zero of a function key on your calculator, that there is a sign change between -2 and -1. And in particular, when we solve it, we see that x is equal to -1.521 rounded off to the 3 decimal places that we were given in our instructions. So with the combination of the intermediate value theorem and using the graphing calculator, you can find those values in between the endpoints of our interval. Well, okay then. In this lesson, we learned about continuity, discontinuity, and the intermediate value theorem. Be sure to work the exercises that your teacher assigns, and we'll see you next time.